and ask Francis to please introduce the next speaker.
Thank you. And Yang, you can go ahead and put up your screen. The next speaker is Dr. Yang, who got his PhD in Steve Buchwald's lab at MIT. And there's a really good advantage to having somebody from that lab because they know all the things that can be done, but also the things that can't be done. So Yang came with a really strong background in transition metal catalysis. After a short period as a Miller Fellow at Berkeley, he joined us because he decided catalysis was what he loved best. And I'll just say, he is joining UC Santa Barbara in about a month from now as an assistant professor. So he's a new member of our academic community and has done really lovely work. Yang, it's now yours. Be sure to unmute. I don't know about anybody else, but I can't hear Yang. So are you?
Great.
Okay.
I just unmute my.
Okay.
Thanks, Francis, for the very kind introduction. Hi, everyone. Today it's my great pleasure to tell you about the recent progress in Arnold Lab on the direct evolution of P450s for asymmetric CH amination reactions. So the Arnold Lab has been very interested in P450 enzymes. It's almost been 2 decades. So these P450 enzymes use the heme cofactor for all of its native functions. And very interestingly, all of these enzymes use iron, the most abundant transition metal in Earth's crust, for all of this interesting chemistry. This fact itself is quite interesting if you are a synthetic chemist. So P450s are found in all kingdoms of life, and they're responsible for a variety of important biological processes. Most importantly, for P450s derived from human beings, they're responsible for the metabolism of 70 to 80% of drugs, and this makes these enzymes very important for the biomedical sciences. P450 enzymes are also excellent biocatalysts. These enzymes are fully genetically encoded and easily expressed. And very importantly, a variety of genes have been known for these enzymes. And to date, more than 300,000 genes are known for these enzymes. And this provides us an excellent opportunity for catalyst discovery. So use this iron oxo intermediate, which is also known as compound 1 in the bioinorganic literature. P450 enzymes can catalyze amazing CH hydroxylation reactions. And here I'm going to show you 2 examples of such CH hydroxylation reactions catalyzed by P450s. And the first example is taken from the biosynthesis of picromycin. And with this particular P450, PIC-C, this tertiary CH bond adjacent to an enone moiety can be selectively hydroxylated, and this converts this very advanced intermediates into the final natural product. In the second example, with an engineered P450 variant, this completely unfunctionalized hydrocarbon can be hydroxylated with excellent subterminal selectivity, and the secondary alcohol forms with excellent enantiomer selectivity. I think these levels of selectivity is going to be challenging to access with small molecule catalysts. So starting from almost 6 years ago, the Arnold Lab became very interested in exploring the unnatural activity of these P450 enzymes. So as a group, we saw the structural similarity between this iron oxo intermediates with these iron carbene and iron nitrene intermediates involved in human invented chemistry. And inspired by the rich chemistry of these iron porphyrin complexes, we started to question whether we can also generate these iron carbene and iron nitrene species within a P450, and more importantly, can we transfer these carbene and nitrene species to organic substrates? Over the course of the past several years, the lab has been able to develop a range of P450s for the selective CH alkoxylation reactions. And CH alkylation reactions and also CH amination reactions. And in this research, the replacement of the iron-bound axial cysteine ligand is very important. And we found by replacing the cysteine residue with an axial serine, these enzymes, these P411 enzymes confer excellent activity for nitrogen and carbene transfer. So today I'm going to focus on CH amination reactions. And biocatalytic CH amination was pioneered by several previous lab members of the Arnold lab, including John McIntosh, Todd Heister, and Chris Pryor. I think both John and Chris are now in the biocatalysis group at Merck, and perhaps they're here with us today for the symposium. So together, the previous lab members found with sulfonyl azides as the nitrogen precursors, P411s can allow for CH amination both intramolecularly and also intermolecularly. And in addition to the work from our lab, Rudy Fassan's group at Rochester has also done very important work in the same area. So before I talk about the recent progress in our lab on CH amination reactions, I'd like to take one step back and show you the overall research philosophy of our research. At this point, you might wonder, how do we create enzyme activity that's not presently known in nature? And the answer to that question is related to a very important concept in biochemistry, namely promiscuity. So enzyme promiscuity refers to the ability of enzymes to catalyze reactions other than the ones they are physiologically evolved for. Although enzymes are widely perceived as very specific catalysts, a lot of these enzymes is in fact promiscuous, and they have the extra talent to allow for unnatural reactions. Enzyme promiscuity is very important in the emergence of new biochemistry in the history of evolution. In our lab, we also try to take advantage of enzyme promiscuity, and just like what's happening in the history of evolution. In our research, we usually start by evaluating a collection of enzyme variants in our lab. And our research is always guided by our understanding of synthetic chemistry and organometallic chemistry. With a very small amount of initial activity being identified, we will then use directed evolution to further improve the activity and selectivity of these catalytic processes. I guess to this audience, I really don't have to introduce direct evolution. I just want to point out that direct evolution is a very powerful tool for the optimization of enzyme function through iterative rounds of mutation and screening or selection. So when I joined the lab, I was very interested in using these P450s to address current challenges in CH functionalization processes. So due to the ubiquity of these CH bonds in organic molecules, CH functionalization has the potential to simplify organic synthesis. I think the stereoselective functionalization of sp3 hybridized CH bonds lies in the current forefront of CH functionalization. And in principle, 3 types of stereoselective CH functionalization reactions can be developed. In the first process, starting from a substrate with pro-chiral secondary CH bonds, enantioselective CH functionalization is going to provide a product with a tri-substituted stereocenter. In the second process, starting with a starting material with geminal dimethyl substituents, the functionalization of the primary CH bonds in the starting material can afford a product with a quaternary stereocenter in it. Furthermore, if we could convert these tertiary CH bonds in racemic starting materials in an enantioconvergent convergent fashion, we will be able to arrive at products with a tetrasubstituted stereocenter. And importantly, due to the lack of highly selective catalysts and suitable mechanism, these enantioconvergent CH functionalization reactions has been very challenging. With all of these difficulties in mind, it will be great if we can have a general enzymatic platform for all 3 types of asymmetric CH functionalization reactions. So with our expertise in CH amination, I'd like to further challenge our P450s for these 3 types of CH amination reactions. So we focus on the synthesis of these chirodiamines to evaluate the use of these P450 enzymes. In this process, we would first append the sulfonyl unit to this easily available aliphatic amine starting material. And with that sulfonyl azide species, the biocatalytic CH amination is going to provide this cyclic sulfonate as the product. And the extrusion of the sulfonyl unit using known chemistry is going to finally provide these chirodiamine products. I'd like to point out that we're not the first ones to come up with this idea, and our research is inspired by the very important work from the synthetic community, especially the work from Dubois, Zhang, Davis, Katsuki, Chi, and many other research groups. Although there's a lot of important work being done, I think there's still plenty of problems to be solved for these asymmetric variants. From a synthetic utility, the synthesis of these chirodiamine species is going to be useful. And this is because these chirodiamines are found in many medicinally active species. And the juxtaposition of the 2 amino substituents in the same molecule created a very specific synthetic challenge. Previously developed methods for the synthesis of monoamines do not necessarily translate to the asymmetric preparation of these chirodiamines. So to get our research started, we look into the enzymatic formation of these 1,2 diamine derivatives. After we evaluate panel of P450 enzymes we collected, we found a few hits. And with this particular P450 variant, 450 total turnover numbers was observed for the desired CH amination product. And the product also formed with good enantiomer selectivity. We named that P450 BM3 variant to be P411-diane1, which stands for diamine synthase. And that particular P450 variant is derived from Kelly's previous carbon transfer lineage. This P411-diane already bears 22 mutations relative to the wild-type P450 BM3, and it lacks the FAD domain needed for the native oxygenase activity. Although the initial chemoselectivity for the CH amination product over the reduction product was quite low, it provides us an excellent starting point for our evolution efforts. With this, we targeted a few amino acid residues in active site by using site saturation mutagenesis. So site saturation mutagenesis and screening allowed us in several rounds of engineering to improve the activity, enantiomer selectivity, as well as the chemoselectivity for the desired CH amination reaction. And our P411-diane lineage is effective for the synthesis of various 1,2 diamine derivatives. In addition to this, several other 1,3 diamine products can also be synthesized with excellent enantiomer selectivity. In terms of the reactivity, the bond dissociation energy of these unactivated secondary CH bond is about 98 kcals per mole. And this is almost about 10 kcals per mole higher compared to the activated benzylic and allylic CH bonds. Nonetheless, our P450s is still effective for the asymmetric amination of these unactivated CH bonds. And most importantly, with 2 P411 variants that are only a few mutations away from each other, we can access either the S or the R enantiomeric product with good enantiomer selectivity. In this effort, the mutation at residue 87 was found to be very important, and a single A87I mutation inverted the absolute stereochemistry of the diamine product. In previous research, this 87 residue is known to be very important in controlling the stereochemistry of the native oxygenation reaction as well as the previously developed carbon transfer processes. And with this initial result, further engineering allowed us to improve enantiomer selectivity all the way from 44% to 96%. And similarly, the enantiomer selectivity for the other enantiomer can also be optimized by further engineering. In terms of the bond dissociation energy, the BDEs of these unactivated primary CH bond is close to 100 kcals per mole. So reactivity-wise, the amination of these unactivated primary CH bond is going to be more challenging. Nonetheless, these P450s can still allow for the asymmetric amination of these primary CH bonds. And with this particular P450 variant, this desymmetrization process occurred to afford the product with a quaternary stereocenter in it. Based on our own study and also literature evidence on related iron catalysts, we think this iron catalyzed CH amination involves a radical mechanism. So starting from this racemic starting material, we're going to form an iron nitrenoid species after the loss of the dinitrogen. So with this, we think this iron nitrenoid species is effectively a diradical species. So following hydrogen atom transfer, we're going to have a carbon-centered radical. At that stage, if the CN bond forming step is highly selective and relatively slow, we're going to be able to convert both enantiomeric starting material into the same major enantiomer. And this provides a very exciting opportunity for us to develop such enantioconvergent CH amination processes. Indeed, we're able to evolve these P450s for the enantioconvergent amination reactions. And after 3 rounds of site saturation mutagenesis and screening, we could optimize this process. This provides the 1,3-diamine products with a tetrasubstituted stereocenter in it with excellent enantiomer selectivity. At that stage, we decided to further challenge these enzymes with very difficult problems known in asymmetric synthesis. So for asymmetric catalysis, the formation of such methyl-ethyl stereocenter is known to be very difficult due to the very small differentiation of the methyl and ethyl groups. Nonetheless, this is not a problem for enzymes, and after 5 rounds of protein engineering, we could optimize the enantiomer selectivity for this CH amination reaction, and EE went from 50-ish all the way to 87%. I think this example really speaks to the power of directed evolution in solving some of the most challenging problems in asymmetric catalysis. So moving forward, expanding all of these interesting intramolecular activity to intermolecular processes is going to be definitely very interesting. And among various intermolecular CH amination reactions, the preparation of these unprotected primary amines is going to be very interesting. And this is because these primary amines are found in numerous small molecule therapeutics, and they're also key intermediates to a variety of other important agents. From a reactivity standpoint, the CH amination reaction to provide these unprotected primary amine is a known challenge. And the majority of the previously developed process all afforded tosyl-protected amine as the product. With these processes, the deprotection of the tosyl amine product is needed to convert these compounds into the primary amine. And even with small molecule catalysts, the direct synthesis of these primary amine products is not known with CH amination strategies. So 2 of my lab mates, Zhijun and Shilong, took this challenge. And based on our previous work in using these hydroxylamine esters for amino hydroxylation reactions, they were very successful for the CH amination process. So starting from a P411B2 variant derived from Chris Pryor's previous nitrogen transfer lineage, Zhijun and Shilong could optimize primary aminases for the conversion of both benzylic and allylic CH bonds. So with their evolved P411BPA and P411APA, a variety of these simple hydrocarbon starting materials can be converted into the value-added enantiomer-enriched primary amine products. I think this is a very exciting result, and it very nicely complements the previously developed biocatalytic strategies for the synthesis of these amines. In the future, through further protein engineering, I think we could potentially achieve the primary amination of unactivated sp3 hybridized CH bonds. And in the longer term, using directed evolution, the activity and enantiomer selectivity of these primary aminases could eventually emulate that of the native P450s evolved for analogous CH hydroxylation reactions. So with this, I'd like to conclude my talk by thanking Francis for being an amazing advisor. I also want to thank the entire Arnold lab for support, and especially people from Team Nitrine. With that, thank you very much for your attention. I'm happy to take any questions if you have.
Thank you very much for your presentation. Are there any questions? And may I please remind everyone to use the hand raise feature for the questions. Nick, please.
Hi, great talk, Yang. So in the diamine chemistry, the first part of the talk, you get very high regio selectivity for CH insertion, which is very interesting. You essentially, I think, are pretty much making 1,3 diamines. So my question was, do you ever see insertion at the adjacent CH bond to give what would be a 1,2 diamine product? Because it seems to me, I'm not specifically familiar with that sort of sulfonyl system, but it looks like the adjacent carbon should also, in principle, be amenable to CH insertion.
Mm-hmm. Yeah, that's a very good question. Yeah, I think here, the sulfomoyl azide starting material played a very important role in dictating the inherent reactivity of these starting materials. So here, if you have the sulfonyl group attached to the azide, then the inherent selectivity is going to favor the 1,3 diamine product or the 6-member product. If you replace the sulfonyl group with a carbonyl group, then I think the inherent selectivity is going to favor the 1,2 diamine product. With an enzyme, the site selectivity for CH amination is potentially tunable. So in my preliminary data, so if here we have a propyl group instead of a methyl group, so I've seen both the 1,3 diamine formation and also the 1,2 diamine formation. Here in this case, the site selectivity is going to be completely dictated by the choice of the enzyme catalyst. I think in the future it's possible for us to further improve the selectivity of these processes.
Have you ever tried the substrate with the terminal alkene, which would then activate the allylic position, and it couldn't then do the 1,3? It would have to do the adjacent CH insertion if you have an alkene at the end. Maybe you tried that.
Are you referring to starting material or processes like this? So
yeah, but force it to go to the 5-membered ring, maybe.
Mm-hmm. So like here, if you cut off one methylene unit, I think we have a chance to access the 1,2 diamine product in this way.
Yeah, maybe. Okay, thank you.
Thanks.
Thank you. Marian, did you have a question?
I did. Thank you, Birgit. Thank you, Yang, for this was great. I've always been wondering, is there a way to get away from the azides and the hydroxylamines? Because on scale, both of those types of reagents are not the super greatest. And so things like Bach amine plus oxygen would be my personal favorite, but what are your thoughts?
Yeah, so for this unpublished work from my lab mates, they've been able to use these hydroxylamine esters as the nitrine precursors. I think this is going to be a very important advance because these hydroxylamine esters are very easily synthesized from hydroxylamine itself, and they can be made on a very large scale. So in terms of the practicality of the method, I think these intermolecular CH aminations using hydroxylamine ester derivatives is going to be important. So for my work, I guess it's more a demonstration of concept, or it's more on the fundamental aspects of possibilities for asymmetric catalysis.
Sabine, last question.
Thank you. This is fantastic work. Can I just ask a slightly general question? I mean, you do these amazing rounds of evolution and get incredible selectivity. Maybe can you just share with us a little bit about what methods do you actually use to sort of analyze the variance these days, and how much do you use sort of machine learning to really interpret your data?
Mm-hmm. Yeah, so for the work that I've talked about today, it mostly based on empirical optimization or directed evolution. So in our research, we usually use site saturation mutagenesis for the generation of enzyme libraries. But in the past, we've done error-prone PCR mutagenesis for random mutagenesis. And I think all of our nitrogen transferases and carbene transferases are based on our variants derived from CH hydroxylation reactions. And that particular CH hydroxylation variant was identified through random mutagenesis. So I would say it's a combination of error-prone PCR and also site saturation mutagenesis. In terms of the screening technique we rely on, we usually do HPLC screening or GC screening. In terms of the throughput, it's not amazingly high throughput, but for HPLC analysis, we're able to analyze one sample within 4 to 5 minutes. So for us, it's been good enough for us to identify beneficial mutations.
Thanks very much. Very good work. Thank you.
Thank you.
Thank you very much. I'm now happy to introduce the final speaker, Alicia Schultz from